Welcome to the Pony session. From my point of view, the Pony endeavor started in 2011 when Sylvan came to Imperial College, said he wanted to do a PhD, and he wanted to develop a programming language where it would be easy to write safe programs. Safe programs, they should be memory safe, type safe, exception safe, and in particular, concurrency should be correct. It should also be possible to write those programs easily. They should have all the necessary abstractions, object-oriented programming, functional programming, and most particularly actors and asynchronous method calls. And it should not be very expensive to run those programs, so we should have all the necessary features in order to make those programs run fast. So here is my first reaction. These features are already known, Sylvan. We have been dealing with them in the last couple of decade or so, and Sylvan answered, no, I believe that if we rethink them from scratch, and if we not only adapt them, but also think how we combine them, we can get to something better. And such a thing would have a horrendous performance. And again, Sylvan's reaction was, if we think about all the abstraction levels at the same time, then we can improve the performance. And if we use the language features in order to get the low level to run better, then we can make it run faster again. So at this point, my reaction was, I don't believe you. I have grown up with a Cartesian approach to things, but let's see. So we started the endeavor. We had great time. We have made quite a few interesting discoveries, I think. And 2 years ago, a student, Sebastian Blessing, joined us, and he was totally convinced, and he said, we have to start a company, we have to start implementing it now. And he convinced us, and we convinced some angel investors, and we started the company. So we started the company 13 months ago. Now we have got the compiler, we have got tools, we have got wonderful results, I believe, and we are very excited to have the opportunity to talk to you about this. And I want to pass on to Sylvan.
Hi everybody, thanks for coming. So, ponies. Yeah, so if anyone wants to know why it's called Pony, I'll explain it to you later. So let's start with actors. Concurrency is hard. We all know concurrency is hard. We've been dealing with it for a long time, but 40 years ago, Carl Hewitt kind of solved this problem. Now, I don't mean he solved it in terms of performance, but he kind of solved it in terms of the mental model we need in order to build software that mirrors what the hardware actually does under the hood. So in a parallel setting, actors are units of sequentiality, right? It means you can write these lovely little sequential programs that do exactly what you expect them to do. But if you want an actor to hold state for everything that's sequential, that means you want to use a lot of actors. And I don't mean tens of thousands of actors, I mean tens of millions of actors, probably churning over a long-lived application. So this is just Hello World and Pony. The point of this slide is the sandbox. If anybody wants to whip out a laptop and experiment with Pony code while I'm talking, please go ahead. That's all online. Oh, is it not working?
Yeah.
Sorry about that.
So lots of actors means lots of messages. And lots of messages, if they're going to be fast, they have to be zero-copy messages. If we're going to do this like Erlang and copy everything, we're going to pay the price that Erlang pays, and that's not interesting because Erlang is already awesome and already does what it does extremely well. So we've got to do better than that. But if we're going to do zero-copy messaging, it's got to also be safe because we can already do this in C++. There's a, for example, the C++ Actors framework, which is a really nice open source project, does this in C++, but it's not safe. So we want both. So what we're using is reference capabilities. So a lot of people who've worked on reference capabilities. There's a big list here. Tobias is even in the back of the audience right there. Anyway, so what these are type qualifiers. Now, there's been a lot of different research on how to use this. So type qualifiers like const, right? Only a lot more powerful stuff that you can do with reference capabilities. So our reference capabilities are based on deny properties. It's all about the existence of this reference denies other aliases from existing in your program statically. Check the compile time, so you know that you can reason locally about these things. So let's look at the big matrix. The things that we need to deny are pretty straightforward. They're exactly the things that Philip Haller already talked about in his research. We need to deny read-write aliases, right? That's a thing. But a different thing is denying write aliases only, and another thing is what if actually it's okay to allow all aliases? And we need to differentiate between whether those aliases are held by the same actor locally or by some other actor globally, because those are pretty separate things. So the first thing is that we're not going to deny things locally that are allowed globally, because that doesn't make a lot of sense, because they can be passed back to the local actor. So we're going to X those out. Those aren't interesting. And we're going to talk about these. So yeah, it turns out we've got mutability, immutability, and opaqueness as separate categories of reference capabilities. So let's start with the sort of straightforward ones that we're all pretty comfortable with. If you can deny global read and write aliases, then it's safe for you to just mutate the object as if you were writing Java and had some mutable object. That's what a reference type is, a ref in Pony. It has a little bit more interesting guarantee because in Java you can't prove that other people aren't reading from it. You can't prove that they're not mutating it. And here, Pony makes that guarantee. By the way, feel free to ask questions in the middle of the talk. That's all right. I'll answer stuff. Then we have value types, global immutability, things that you know you've denied write aliases both globally and locally. So there are no write aliases remaining in the system. That's great. Immutability, global immutability. Then we have box, sort of a black box type, where by denying global write aliases but allowing all local aliases, you're saying this is locally immutable. I'm not going to mutate it here, and I know I can read from it because no other actor is going to write to it, but I'm not going to guarantee that this actor isn't going to write to it. That's pretty useful. It turns out it's probably the most used type, right? It's things you want to read from, and you don't really care about what's going to mutate it. Then we have a pretty straightforward type in some ways, which is tag. It's an opaque type. These are things you can neither read from nor write to. So why is that useful? Well, identity, obviously, object-oriented programmers, it's pretty powerful to be able to ship that concept of identity across concurrency, across actors. Also, an actor itself, when you send it an asynchronous message, that's not reading, that's not writing, so you can type actors as tag. Then we have the fun ones, isolated. Isolated is read and write unique. This is the only alias through which you can either read or write. Not just the thing itself, but because it forms a bubble, all of the things that it reaches, with some interesting exceptions about being able to reach immutable things that are reachable by an isolated thing. External uniqueness. Separate uniqueness, I should say. Then we have transition types. This is kind of fun. I thought this was an artifact of the matrix, and I thought these weren't interesting types. It turns out this is a write unique type, which is kind of fun. It means that we know this is the only write alias, but we're not making any claims about it being the only read alias, which turns out to be more interesting and powerful than I thought at first it would be. So there we go. We have 3 kinds of mutability, 2 kinds of immutability, and a kind of opaqueness. But we also have sendability. So when you're denying local aliases in the same way that you're denying global aliases, those are things you can send in messages to other actors, because those are things that are making the identical guarantee locally that they're making globally. When those guarantees aren't the same, communicating them would be unsafe, but here you can. So you can send tag things, pretty straightforward. It's just an identity. Obviously, everyone can have that. Send immutable things, globally immutable things. Yeah, of course. But you can also send isolated things. You can send mutable state safely across actors. That's fun. Aliasing, turns out, is a thing here. Because what local aliases can exist are based on the deny properties. So for example, let me back up one. So for example, local aliases for a transition type. Because it's write unique, because of what it denies, which is to say local write and global read and write, you can only have things that obey those deny properties as aliases. So it's okay to have a tag. Everything's okay to have a tag, right? Because those neither read nor write, so you can have a tag alias to anything. But you can also, funnily, you can have a box alias to a transition type. So you can locally keep readable references to this thing that is write unique. So you can be write unique for a while, and later you can give up some of those capabilities and become globally immutable while not caring about the fact that you had these locally immutable references hanging around. They're still valid. So that's kind of fun. And the same thing goes with global aliases. There's another set of what global aliases can exist underneath. This is pretty straightforward. What it tells you is that immutability is for sharing, and isolation is for passing. That's good. So cognitive load. That's a lot of stuff I just covered. And to say that the programmer is just going to happily go and add these kinds of annotations to their programs and everything's going to be fine is obviously not, strictly speaking, true. On the other hand, we've had better luck with this than I expected. Programmers, and we're talking about hobbyist programmers here, people who like hop on the IRC channel and say, I want to write a package in Pony to do JSON parsing. Awesome, guy really did that. A bunch of different packages, actually. And generally, the pattern goes like this. They get on, they say, Pony looks really easy. I'm going to write a bunch of code. This is awesome. This is crap. None of this works. I don't understand how to use any of this. And then they ask a few questions, and after maybe a couple of weeks on the outside for hobbyist programmers, they're really comfortable with it. They're not actually overloaded. A lot of this has to do with using sane defaults for types, and so that a lot of the annotation happens to disappear. It mentions in about 20%. That's in the standard library that we're using, about 20%. To be honest, in people's code that they're writing themselves, it's probably less annotation. The standard library is pretty aggressive about using interesting annotation. So aliasing and unaliasing, we mentioned about things that are unique, or read and write unique, can't aliases themselves. So we need a concept of being able to recover capabilities and consume capabilities. Because otherwise, what are you going to do with that isolated thing? How are you going to send it when you still have a reference to it? So this is pretty straightforward. Here's Hello World rewritten, pretty pointlessly, but still rewritten, to use an isolated string instead of an immutable string. So we have a recover expression, which is building a mutable string, a string ref. But when it returns it, it recovers capabilities. And what it recovers to, I'm going to back up just a little bit here. It recovers to the top thing on the matrix for the type that it is when the expression terminates. So that a ref can be read and write unique, a box can end up immutable, things like that. So, and consume does exactly what you'd expect it to do. You kill it out of the lexical scope, out of that name, and that means you've killed off a name, which means you've killed off an alias, which means that now you have the unaliased version of that type. Oh, sorry. So I'm gonna mention a little bit how unaliasing works, especially in the presence of polymorphism, where unaliased type parameter annotation gets to be kind of fun and interesting. So capabilities security. In the type system literature, this stuff is often just referred to as capabilities. After talking a bunch with Mark Miller and a bunch of other people who have done capability security research, we've decided to use the term reference capabilities to try and draw a little bit of a distinction about what this is. Now, reference capabilities are a form of capability security, but in Pony, we're also talking about object capabilities in the object capabilities systems research sort of level. So reference capabilities are attached to the path of an object, not to the object, right? I have a ref to this, and you have a box to that, and that's fine. Nothing is encoded at runtime in the object about that. That's all compile time information. But object capability is about what the object can do, the unforgeable token that represents access to that object and the methods that you can have on it. So Pony combines these two things to get some really fun concurrent object capabilities security, and is a capability secure language, which is really fun. All right, more things we're going to do. We're going to avoid runtime exceptions. So we want to, as Felix was saying in his talk on Rust, leverage these programming language research features. We want a non-null type system, safe constructors, right? Finishing a constructor without initializing all your fields, that should clearly be a compile time error. That's pretty straightforward. If we have a non-null type system, what do we do about linked lists and stuff like that? Well, we need algebraic data types. You can use union types as a form of option type. We have checked exceptions without signature explosion, so Pony uses partial functions as opposed to more traditional throw mechanisms. I won't really cover that today. Obviously, you can still run out of memory. If you want to smash your stack or allocate out of the heap, we're not solving the halting problem. We're not going to prove that your program is safe in all these circumstances. But we're covering a lot of other fun stuff. So now let's get off these fundamentals and into some of the things that make Pony more usable than you might expect, at least I hope than you might expect. Obviously, generics, when you're dealing with object-oriented programming, I think punting on generics is an unfortunate choice, so we didn't do that. But that means that we also need capability polymorphism, which is kind of fun. And this is what I was mentioning before about annotations for the unaliased version of a type and the aliased version of a type. So here's an example. I left out the implementation, but this is from the standard library. The array is obviously implemented in Pony. And here we're going to initialize an array where everything is set to the same initial value. But that value has to be something that can alias as the thing that we have an array of, right? Because if I say we have an array of isolated strings, for example, and I say set them all to this same string, we have a problem. We have multiple copies, we have multiple references to that same isolated thing. So this says, you can't pass me the thing that I'm an array of. You have to pass me something that will alias as the thing that I'm an array of. And similarly down below, I'm going to skip over this because this gets a little bit more complicated. But the one on copy 2, the destination is a ref array, something that we can mutate because we're going to copy into it. But it's not an array of A. It's an array of things that the array that we're dealing with right now, how it would see them. So for example, if we were calling copy 2 with an immutable array, it would be how an immutable type saw its element type, which is viewpoint adaptation, if you're familiar with that stuff. And not only that, it has to be an alias of it, because we're not deleting them from the existing array. So that gets interesting, too. So, traits, nominal typing. Pony is an object-oriented language for sure, but it's not an inheritance-based language. It's a trait-based language. So this is based on excellent work that already exists. We do some override alias. We don't do removing methods at this point. We've considered it, but we don't seem to have a use case for it yet. No state. Traits don't have state in them. Ambient talk, for example, has traits with state in it, and that's quite interesting, and maybe it's something we could learn from ambient talk. We haven't done it yet, but it's something interesting we can look at. But we also have structural typing. Similar to Go interfaces, but they're obviously polymorphic, and they give programmers a nice dynamic feel to what otherwise is a pretty statically typed, well, entirely statically typed and a bit constricting language. But when you just say, I only want an object that conforms to basically this, and I don't want to have declared it in advance, and I just want an interface, something like this, that's really nice for the programmer. But that's not why we did it. The reason we did it is that one that I've glossed over in the middle there. Variance on type parameters is hard. Java got that perhaps slightly wrong. Other languages have got it perhaps slightly wrong. Scala covered it, I think, quite perfectly and in detail with co- and contravariance annotations on parameters. But to say that that can be somewhat unwieldy for the programmer, I think, is not a controversial statement. And so in Pony, what we use is structural typing for that. You can have a structural type that says, you know what, all I need to be able to do is, say, read from some sequence. It has to behave like a sequence, and I want this type back. And there are lots of things that are going to behave like that. And when you've limited yourself to that interface, you maintain soundness. So that's nice. So functional features. Sophia mentioned that we want those too. Well, yeah, I want those too. Come on. So type expressions, algebraic data types, union types, intersection types. Intersection types are really fun and powerful. Tuples as well, built into the language, not a form of sugar, but actually built in. Polymorphic types, polymorphic methods as well, obviously. But also partial application, lambdas, object literals. Not only that, but we get some really nice, interesting behavior on being able to build these things without runtime overhead. So you get lambdas that don't involve allocation and things like that. And then when you're capturing scope, you can capture with a single allocation in kind of fun, interesting, optimized ways. That's really nice. Obviously, pattern matching on type, pattern matching on structural equality, all that good stuff. On the other hand, there's something a little bit interesting about Pony's pattern matching in that it respects the object-oriented encapsulation boundary. Scala's work on case classes is really fun and interesting for this, and I think a nice step in the right direction. I hope we've done something even more fun, which is you can do this arbitrarily on objects. You don't need case classes. But you don't automatically destructure objects. Those objects have to expose destructured fields. Yeah, go for it.
Scala has extractors.
Yes, exactly. Sorry, I probably glossed over that too fast. Scala's case classes and extractors are exactly the inspiration for this stuff. Absolutely. So, but it turns out really my background is in low-level C hackery, not in type systems and not in programming language theory. That's all new to me. So I want to have my cake and eat it, right? This is not about building a language that's safe and has all these high-level features. This is about building a language that scratches my personal itch, and my personal itch is a background in large-scale financial systems, video games, physical simulation, cryptography, things like this. Things where performance is really the only metric. There is nothing else, right? It turns out, even in financial systems, robustness takes second place to performance. That's exciting and interesting. So what I want to do here is make sure that all of these high-level features aren't being used to slow the language down, that we can actually use them to take shortcuts, that these guarantees let us cheat. It means we can implement a runtime that absolutely wouldn't work if you didn't have these guarantees higher up in the language. In fact, it would just fall over dead. We would do things that are absurd. But we can get rid of these dynamic checks. We can use actors all the way down and get lots of fun benefits there. Let's start with the scheduler. Obviously, it's work-stealing scheduler, right? Single producer, multi-consumer queues to steal actors, cache-aware stuff. If an actor has pending work and you send it a message, it should stay on the scheduler thread it was on, right? Its working set is probably in cache, if anywhere, on the thread that it was scheduled on previously. On the other hand, if it wasn't scheduled and it gets a message, it should get scheduled on the local thread because its working set probably isn't in cache anywhere. It might be, but you're taking a gamble. And the message that you just sent it is definitely in cache on the thread that just sent it. This stuff, it turns out, matters a lot. The Silk guys at Intel put a lot of work into this kind of stuff, and it's really good work. But we need fast scheduler queues, because scheduler queues are the second worst thing you can get wrong in a runtime for actors. The worst is obviously message queues. So zero atomic ops on push with no loops. That's good. That's great. I'm really happy with that. That's fantastic. On the other hand, 128-bit atomic compare and swap on pop is nothing special, right? That's what everybody's going to get out of an unbounded SPMC queue. Fast message queues, right? So if you send a message to an actor, we're going to do that a lot, right? We mentioned lots of actors, lots of messages, so we want that to be as fast as possible. Here, single atomic operation on pop, no loops. And here's the fun one, one atomic operation on push. 0 on pop, no loops, on an unbounded queue. With previously empty detection on the push. Sorry, this gets a little low level for people who haven't worked on this stuff yet. Please interrupt me if you want to know more about it. Dmitry Vyukov, who now works at Google on the Go runtime, did a bunch of work on these kinds of queues that's really interesting and that we've learned a lot from. Memory allocation. It turns out you can cheat with memory allocation when you have these high-level language guarantees, which is super fun. We have separate heaps for every actor. That means every actor can go and allocate without ever dealing with any kind of coordination of any kind. So not just no synchronization, but no coordination at all. So we have an amortized alloc cost of a CTZ, count trailing zeros, which is good. That's fast. On a cache line aware allocator, yeah?
Do you have segmented heaps?
No, we don't. You mean segmented stacks or segmented heaps?
Yeah, so
segmented stacks.
What happens when the heap grows for a particular actor? Because you have millions of actors, right?
Yes, indeed we do, yeah. So those heaps they're individual heaps, and they can grow arbitrarily large. So we're going to get into the garbage collector in a little bit and talk about how we take care of that, because that's a very important point. Yeah, extraordinarily important point. Yeah. So cache line aware allocation, right? We all need to be doing that, but we get to, again, cheat. We have all these high-level language guarantees. We know a lot more about what that cache layout, and I'm talking about mostly about cache lines here in terms of data layout. We know a lot more about what it's going to look like than you might otherwise know. So we allocate on the local NUMA node. NUMA node awareness is really important on modern systems. You don't get many servers these days that are at least 2 nodes. But actors migrate. So we allocate on the local NUMA node, and then we get rescheduled on some other scheduler thread that had no work, and now we're running on a different NUMA node. So we tried migrating all our pages. If anyone's tried that, you know as well as we do at this point that that's a horrible idea. That's about the biggest performance lose we ran into trying to do this stuff. Leave it alone, it turns out, is the only strategy we've run into. If anyone knows better, please talk to me afterwards. But right now, it looks like the OS handles this better than we can in userland. So, garbage collection, this is Dougley. And did an interesting talk and mentioned some of the things that he's run into with garbage collection. Yeah, blocking, jitter times, things like that. These things are problematic. So, in Pony, when we GC, we have a fully concurrent garbage collection in the sense that we don't even have GC threads. Actors collect themselves only. We have no stop the world, no read barriers, no write barriers, no synchronization, no save points, no stack maps, none of this stuff. And actors are collected as well, which is really nice. And it turns out it's actually sound, bit of a bonus. So doing data race-free GC is where we get most, sure, actors help hugely because we're talking about collecting individual actor heaps, but there are also problems with that I'll get to in a second. But data race-free GC is where we get a huge win. Because we're not dealing with possible data races at the language level, we can take all kinds of shortcuts at the runtime level. So here's where we get into some issues. The per actor GC is great, right? We collect our own heap, but cross actor GC, we were talking about zero copy messaging before, so we've sent pointers across actors that were allocated on different actor heaps. So now we have a problem. Now we can't just start collecting those things. And in actor GC, actors form cycles, right? We're going to collect those actors. Figuring out how to do that is non-trivial. So per actor GC, pretty straightforward. It happens between behaviors. Although, full disclosure, I was talking with Clebsch earlier, and this might not be a great strategy, honestly. It works really well in the stuff we've done so far, but we may want to also do collection during a behavior. Full disclosure. Anyway, but we can do this stuff without looking at the state of any other actor, and even when we do it during a behavior, that's going to hold. None of these things change, it's just going to add some interesting stuff on stack maps and things like that. So, no stop the world step, all that stuff, and maybe we should GC during behaviors. What is that doing? I have no idea. Here we go. Right, so cross-actor GC. This is where we start getting really tricky on the GC side. So deferred, distributed, weighted reference counting is a lot of adjectives on reference counting. Basically what this means is we're using the actor model in the runtime to handle reference counting not based on the shape of the heap. Right? Because I don't care if this object has a reference to this object or if I mutate the heap and drop references, add references, all those things that slow reference counting down in that sense, we're just going to ignore them. We don't care about that. We only care about messages. We only care that I've sent an object that I allocated. And then we need to do interesting things to keep track of when that has been sent on. So, causal messaging. I haven't mentioned causal messaging yet. I should have mentioned it earlier. So the runtime is built on guaranteeing causal messaging. So if A sends a message to B, and subsequent to that, A sends a message to C. And in response to that second message, C sends a message to A. We want to guarantee that A receives message 1 and then message 3. This is a really strong guarantee. Other forms of the actor model make guarantees that are as weak as no ordering at all. This one is a very strong guarantee. Now, on a single node, this is so cheap, it's free. It turns out we can't actually implement a faster message passing system without causal messaging. Fantastic. In the distributed context, which, by the way, is still vaporware with Pony, but I'll cover it a little bit at the end, this is not free. This involves some interesting hackery. Not only that, it might be wrong. Full disclosure, right? There's an interesting concept called E-order that comes out of Mark Miller's research on his language E that might be more useful here. We're not sure yet. Anyway, the point here is that because it's all based on messages, and we have causal messaging, if an actor receives a message that it doesn't own, and receives an object that it doesn't own, that means it wasn't allocated on its heap, and it wants to send it on, it might need to manufacture references and say to the original owner, you need to up that reference count by another couple of thousand just in case I need to send this more later. When you have causal messaging, you can do that without an acknowledgement cycle. That's really nice. So you just pop that message on the queue, single atomic operation, and you send the message on. No delay, no coordination. And no object cycle detection, because we're not keeping track of whether objects have references to the other objects, only whether actors have references to objects. So there's no cycle detector required here. That's good. But actor garbage collection. We want to be able to garbage collect actors because manually managing actor lifetime is unfortunate, right? We've all done it before in other actor model languages, and they're much like collecting regular old object garbage. It's a lot nicer to know that you're never ever going to send a message to a stale reference on an actor. That's good. And also poison pilling actors and all the things that we do. It's problematic, and especially problematic when we start talking about the tens of millions of actors type scenarios that I'm talking about. So we want to collect them, but they have to die when they cannot possibly receive a message in the future. Right, okay. So that's complicated, and it requires cycle detection. Not only that, but because the actor's view of its topology and the cycle detector's view of the topology are both almost certainly out of sync with the real sort of derived topology that you would put together if you could stop the world and figure everything out. we have a problem in making sure all of this works. So this was our OOPSLA paper a couple of years ago. It's not as bad as it sounds. It turns out a cycle detector actor isn't that much of a bottleneck because it's kind of like a GC thread. You can tell it to not worry about things and defer and run in the background. So that's not that bad. And more importantly, the protocol to determine that these things were in some known isolated cycle at the time that the cycle detector was informed about them isn't that bad. It turns out when the cycle detector detects an isolated cycle of actors, all it has to do is send them all a confirmation message with just a token in it that says this is just an ID number. And all those actors do is echo it back. That's it. They don't examine their state. They don't do anything because we don't want to examine state on an actor that might be collected because then you're examining stuff that shouldn't really be in your working set. That's a problem. We don't want to ever look at stuff that isn't in our working set. But when it echoes it back, each time the cycle detector gets that acknowledgement message back for a given blocked actor, if it hasn't received an unblocked message for that actor, it turns out that means we can prove that that actor's view of its own topology was correct at the time that it sent it, and therefore also at the time that the cycle detector received it. So if we get back these acknowledgement messages without an unblocked message for everything in the isolated cycle of actors, we can prove that the topology was correct when the entire cycle blocked. And now we know that we can collect these things. That's pretty fun. Admittedly, this is a message round trip to every actor in the isolated cycle. But our message queues are fast, so it's not that bad. We're talking about 2 atomic operations per actor in the cycle, which in terms of GCing an actor, that's pretty good. So, other things that we want to do for speed. Yeah?
So with the actor GC, do you foresee any potential issues when you start distributing these things?
You bet, absolutely. And the main one is going to be that you're going to want to run these cycle detectors in a hierarchical manner in a distributed system. Obviously, if you run a single cycle detector for an entire distributed system, what you're going to have is the node that you're running the cycle detector on is going to fail, and then you're never going to collect anything ever again. So yeah, you have to run these in a hierarchical manner, and to say that that's straightforward is a big fat lie. But it's not as bad as you'd think, because it turns out, little digression into the distributed side, but it turns out you only ever need to forward a cycle to a parent cycle detector if you examined the cycle and discovered that there's missing incoming references. Everything's blocked, but there's missing incoming references, and you can prove that those missing incoming references come from somewhere above you in the hierarchy instead of below you. So you very rarely have to forward that cycle onto a parent cycle detector, which is nice. So fast dispatch. I mentioned structural types before, and oh yeah, please.
Can messages contain references to actors?
I'm sorry, can you say that again?
Can messages contain references to actors?
Absolutely, yeah. So it's an arbitrary soup of the actor graph is an arbitrary soup and can change dynamically. Yeah, absolutely. Right, structural types. I mentioned structural types before. If there's anyone who's programmed in Go, you'll know that sometimes you have to build a vtable on the fly for an interface, and that's problematic. I'm not familiar with how structural type dispatch in Scala works, but I think it's a little bit complicated. Yeah, that was a good nod. So it turns out we're taking advantage of a paper that Jan Vitek may or may not remember having written 20 years ago about selector coloring. It turns out there's this rather brilliant algorithm in there for being able to do the equivalent of register allocation on your method names. And when you have an ahead-of-time compiled language, like we do, that has all of these static guarantees that we have, we can cheat. And so we can build a single vtable that works for both structural and nominal dispatch, and it's always a single array index. That's pretty fun. Now, obviously, it is a form of a coloring algorithm. You can get into pathological cases where you end up with a vtable that's just too big. That's not solved. How often do we run into it? So far, never. But theoretically, the problem is there, right? So that may be something we need to revisit. We're not sure. So this holds even when you're calling a method, not just on something that's a structural type or a nominal type, but also on a union type or an intersection type. It's the exact same dispatch. It's always single array index and nothing that checks the type at runtime. It's just an array index and go. which is nice. So obviously we use LLVM for code generation. I suspect a lot of people here have hacked on LLVM. If you haven't, find a project to go do it because it's wicked fun. We use it for all kinds of things. But probably the thing that's most exciting to us is that it means that we're capable of handling interesting future architectures. Yeah. Thank you. We can handle interesting future architectures. That's pretty awesome. There's all kinds of heterogeneous architectures that LLVM is going to be supporting that make for really interesting high-performance computing platforms. So some benchmarks, otherwise known as snake oil. We tried so hard to find benchmarks that were somehow useful to people. I hope these are a little bit useful to you. We didn't write our own because that's really problematic. We used them from the C++ actor framework, which we really, really liked. It's a great open source project. So the three that we're going to show here, one is for message queue contention. The other is a combination of message passing and CPU load. And the other one is for actor overhead. How fast can you create a lot of actors? So mailbox performance. So this is a single mailbox being bombarded by 100 million messages from a whole bunch of actors. I'm sorry, I can't remember how many actors are sending the messages, but I think it's, I don't know, 100,000, something like that. And this is the mailbox contention. This is all relative to Erlang on a single core, all these speeds. So we do pretty well. This is good. We're not only faster than Erlang for dispatch on one core, but we're actually maintaining nice mailbox performance even in a really heavily contended system. This is a 32-core machine, and we're running all the way up to 64 hyperthreads. Originally, we thought we weren't going to bother testing with hyperthreads because it's going to kill us, but it turns out it's good. So we're going to show it to you. Hey. All right, so the black one's Pony on the top there. Erlang is a little bit hard to see. It's that slopey green one. We have the C++ actor framework, which is a little bit unfortunate down at the bottom blue. There's Charm++, which is a very interesting supercomputing framework that gets a lot of use. It's not the most modern thing in the world, but it is a well-used and well-known and robust system. It doesn't do that well, and I'm sorry, Philip, but Scala doesn't do that well on this either. So this is message ring and factorization. This is a whole bunch of message load that serves no purpose whatsoever, followed up by a whole bunch of large integer factorization that serves no purpose whatsoever. And the idea is just to make sure you keep the CPU loaded while at the same time you're sending messages and banging on the message queuing system. And we get some interesting profiles here too. That's pretty fun stuff. We're doing pretty well on that. You'll see that our jitter all comes out when we're up at hyper-threading. Our jitter appears to be worse than other people, and I don't know why yet. So that's interesting. Also, caveat, you'll see that we don't have as many results for Scala. We ran out of benchmarking time, so we tried to get some representative core counts. Everything else, it's specific. It's every single core count all the way through. We don't have that for Scala, so we might see some interesting behavior in between there, but I'm afraid we don't have it. Sorry about that. So creating actors. I like this one because we didn't win, and it's really nice when you're showing off snake oil to make sure that not everything is a big win. Here we're creating 1 million actors and seeing how fast we can, in a tree, and they're all, you're doing a big creation, and then they're all echoing messages back to the root. So you can't do anything except wait for this entire tree to resolve, which, based on the fact that we do cycle detection on actors, is pretty much our worst case. This is it. This is the worst possible case for Pony creating a gigantic tree of actors. Normally, you're going to have a graph that's much more susceptible to collection than this. So the C++ actor framework does brilliantly here. Unfortunately, it's not a garbage collected language, neither object collection or actor collection. But they do get great performance results here. That's really good and fun stuff. Pony does pretty well. We do well at first, but we level out a lot sooner. On the other hand, this is doing cycle detection on those actors. So that's pretty good, I think, I hope. Right, enough snake oil. This slide came out yesterday in Gilad's talk, and I buy it. I really do. Unfortunately, I'm not going to claim that Pony is a live environment. It's not. It's about the most dead programming environment you can think of. You're talking about a text editor and a compiler. We don't even have a REPL. I mean, come on, this is dead. So we're trying to do our best to give you tools that make that still useful. So let's see what we've got so far. One thing is fast compile times. Now, right now, in an optimized build, 90% of your time is spent in the LLVM optimizer. People who've used LLVM are probably familiar with that being the case. But that's pretty good. It means that our overall compile times are seem to be, I won't make too many claims, seem to be faster than C on average. Obviously, still slower than Go. Go is the king of compile times. I would love to be as fast as them, but on the other hand, they're only doing single pass optimization, and we're doing whole program optimization. So there's a bit of a difference there. Right, so C ABI compatibility, when you don't have your own ecosystem and you want to do systems level stuff, you better be able to talk to the C ABI directly, and in Pony's case, that means you can also compile an entire Pony program and with the C ABI and have the compiler generate a header file, so you can call it from C as well as the other way around. So that's fun. All this other stuff, editors, direct integration with the debuggers you already know how to use, that's good stuff. Community, we've got a community. Probably the only thing that I really find fun about this slide is that somebody already ported it to FreeBSD for us. Come on, that's awesome. There's a 32-bit x86 port that's being done. Right now, this is 64-bit x86 only, so x64. On the other hand, this 32-bit port seems like it's going to work, which I'm frankly surprised, but it does look like it's going to work. And someone's working on a 64-bit ARM port. Once we have those, we should be able to do 32-bit ARM, so there's all kinds of fun stuff that we'll be able to do. Future, back pressure. Remember all those unordered queues I was talking, not unordered, unbounded queues that I was talking about? Right, well, that means back pressure has to happen at the language level. So that's interesting. Capability secure mirror-based reflection. We want to do a REPL. We're going to do type parameters parameterized on values. That's going to mostly for performance reasons on big matrices. Distributed runtime, if anyone wants to talk to me about that, I will bore them silly, but it's vaporware right now. There's a lot of fun stuff and more formalization. So please, if anyone's interested, get involved. It's all open source. We have mailing list and GitHub issues and an IRC channel. Sometimes we even answer mail on the mailing list. Sometimes. But the IRC channel and GitHub issues, those really work. That's good stuff. So please get involved. So what did we learn from this? Cheating is good. That's what we learned from this. Right? Using the actor paradigm for the runtime is fantastic. Using all of these language level guarantees to optimize the runtime is fantastic. And starting from principles and using formal models actually improved our implementation drastically. Yeah, okay, we closed soundness problems. That's important too. But it actually made the runtime faster. And that's fun. All right, thanks everybody. Yeah.
So what's the origin of the name?
The origin of the name. So first of all, for Americans, a pony is a racehorse, so it has a connotation of the Pony Express and going fast. But actually, that's not why the name is there. The name is there because of the typical conversation you have with people. I want this feature, and I want this feature, and I want this feature, and I want a pony. So there you go.
I have one comment and one question.
Yeah.
So my comment is that when you benchmark all these systems,
Yeah.
it seems to me that there are some of these systems like Erlang and others, they also Akka is distributed
Right.
from the Go. So
Yes.
so I think you probably pay some price there because the whole runtime system has to be
Yeah, I agree with you.
distributed. So yeah.
The only thing, if you want to, I would be really keen to talk about Pony's strategy for distributed runtime with you if you have time at some point. The nice part is the distributed runtime won't change single node performance at all. So I don't feel that uncomfortable with these horrible lying benchmarks, but you're obviously right.
Okay. If you already know that, it's sometimes you have to first do it and then you
Yeah,
know
and
more.
then you realize how much you have to change later.
Right.
No, but we already know that nothing changes on the single node runtime, so that's good.
Okay, that's good.
It's just a prototype. Don't get too excited.
Okay. So my actual question was, because you said, well, you have C interop.
Yes.
So how do you do this, like on the type level with all the different
Oh yeah,
safety
it's
things?
a gigantic trust boundary, right? When we talk about capability security, because right, here we have a capability secure language, and we're going to say you can have a CFFI. So what guarantees can we offer you? We can guarantee you that you're going to crash the hell out of your program. That's what we can guarantee you. So we treat this in a different way. So instead of saying we're going to try and, the way Erlang can isolate C in another process and all these fantastic things for robustness, instead we treat it as the trust boundary. You don't trust it because you can trust it. You trust it because you have to trust it. You don't have any other choice. So the Pony compiler has this notion of safe packages. Safe packages are the packages that are allowed to run CFFI, which is why we can have the sandbox, if anyone wants to look at it, and let you compile native code and run it on our server. We're not worried about it, because only trusted packages can use the CFFI. So you establish your capabilities trust boundary like that. Does that answer your question? All right, great.
So I sort of follow.
Okay, thanks.
Okay, follow up to that. What's your stack representation for your FFI then?
What's our stack representation?
Yeah, how do you deal with that? Are you just gonna? Because I'm assuming you're using. I don't know. You said no segmented stacks, but I don't know what you're using instead of segmented stacks.
We're not. We're actually using CABI stacks. So we're using essentially LLVM fast call internally, and we switch to the C representation when we call it C.
But each actor doesn't have its own stack, right?
Each actor has its own stack, but it only has a stack when it's executing a behavior. So actually, only each scheduler thread has its own stack.
Okay.
Yeah. So on, if you're running 32 scheduler threads, you have 32 stacks and never more. All right. Thanks, everybody.
In order to build software that mirrors what the hardware actually does under the hood. So in a parallel setting, actors are units of sequentiality, right? It means you can write these lovely little sequential programs to do exactly what you expect them to do. But if you want an actor to hold state for everything that's sequential, that means you want to use a lot of actors. And I don't mean tens of thousands of actors, I mean tens of millions of actors, probably churning over a long-lived application. So this is just Hello World and Pony. The point of this slide is the sandbox. If anybody wants to whip out a laptop and experiment with Pony code while I'm talking, please go ahead. That's all online. Oh, is it not working? Yeah. Sorry about that.
So lots of actors means lots of messages. And lots of messages, if they are going to be fast, they have to be zero-copy messages. If we're going to do this like Erlang and copy everything, we're going to pay the price that Erlang pays, and that's not interesting because Erlang is already awesome and already does what it does extremely well. So we've got to do better than that. But if we're going to do zero-copy messaging, it's got to also be safe because we can already do this in C++. There's a, for example, the C++ Actors framework, which is a really nice open source project, does this in C++, but it's not safe. So we want both. So what we're using is reference capabilities. So a lot of people who've worked on reference capabilities. There's a big list here. Tobias is even in the back of the audience right there. Anyway, so what these are type qualifiers. Now, there's been a lot of different research on how to use this. So type qualifiers like const, right? Only a lot more powerful stuff that you can do with reference.
Welcome to the Pony session. From my point of view, the Pony endeavor started in 2011 when Sylvan came to Imperial College, said he wanted to do a PhD and he wanted to develop a programming language where it would be easy to write safe programs. Safe programs, they should be memory safe, type safe, exception safe, and in particular, concurrency should be correct. It should also be possible to write those programs easily. They should have all the necessary abstractions, object-oriented programming, functional programming, and most particularly actors and asynchronous method calls. And it should not be very expensive to run those programs, so we should have all the necessary features in order to make those programs run fast. So here is my first reaction. These features are already known, Sylvan. We have been dealing with them in the last couple of decade or so, and Sylvan answered, no, I believe that if we rethink them from scratch, and if we not only adapt them, but also think how we combine them, we can get to something better. And such a thing would have a horrendous performance. And again, Sylvan's reaction was, if we think about
mutating it, and here Pony makes that guarantee. By the way, feel free to ask questions in the middle of the talk. That's all right. I'll answer stuff. Then we have value types, global immutability, things that you know you've denied write aliases both globally and locally. So there are no write aliases remaining in the system. That's great. Immutability, global immutability. Then we have box, sort of a black box type, where by denying global write aliases, but allowing all local aliases, you're saying this is locally immutable. I'm not going to mutate it here, And I know I can read from it because nobody else, no other actor is going to write to it, but I'm not going to guarantee that this actor isn't going to write to it. That's pretty useful. It turns out it's probably the most used type, right? It's things you want to read from, and you don't really care about what's going to mutate it. Then we have a pretty straightforward type in some ways, which is tag. It's an opaque type. These are things you can neither read from nor write to. So why is that useful? Well, identity, obviously, object-oriented programmers, it's pretty powerful to be able to ship that concept of identity across concurrency, across actors. Also, an actor itself, when you send it an asynchronous message, that's not reading, that's not writing, so you can type actors as tag. Then we have the fun ones, isolated. Isolated is read and write unique. This is the only alias through which you can either read or write. Not just the thing itself, but because it forms a bubble, all of the things that it reaches, with some interesting exceptions about
all the abstraction levels at the same time, then we can improve the performance. And if we use the language features in order to get the low level to run better, then we can make it run faster again. So at this point, my reaction was, I don't believe you. I have grown up with a Cartesian approach to things, but let's see. So we started the endeavor. We had great time. We have made quite a few interesting discoveries, I think. And 2 years ago, a student, Sebastian Blessing, joined us, and he was totally convinced, and he said, we have to start a company, we have to start implementing it now. And he convinced us, and we convinced some angel investors, and we started the company. So we started the company 13 months ago. Now we have got the compiler, we have got tools, we have got wonderful results, I believe, and we are very excited to have the opportunity to talk to you about this. And I want to pass on to Sylvan.
Hi everybody, thanks for coming. So, ponies. Yeah, so if anyone wants to know why it's called Pony, I'll explain it to you later. So let's start with actors. Concurrency is hard. We all know concurrency is hard. We've been dealing with it a long time, but 40 years ago, Carl Hewitt kind of solved this problem. Now, I don't mean he solved it in terms of performance, but he kind of solved it in terms of the mental model we need in order
capabilities. So our reference capabilities are based on deny properties. It's all about the existence of this reference denies other aliases from existing in your program statically. Check the compile time, so you know that you can reason locally about these things. So let's look at the big matrix. The things that we need to deny are pretty straightforward. They're exactly the things that Philip Haller already talked about in his research. We need to deny read-write aliases, right? That's a thing. But a different thing is denying write aliases only, and another thing is what if actually it's okay to allow all aliases? And we need to differentiate between whether those aliases are held by the same actor locally or by some other actor globally, because those are pretty separate things. So the first thing is that we're not going to deny things locally that are allowed globally, because that doesn't make a lot of sense, because they can be passed back to the local actor. So we're going to X those out. Those aren't interesting. And we're going to talk about these. So yeah, it turns out we've got mutability, immutability, and opaqueness as separate categories of reference capabilities. So let's start with the sort of straightforward ones that we're all pretty comfortable with. If you can deny global read and write aliases, then it's safe for you to just mutate the object as if you were writing Java and had some mutable object. That's what a reference type is, a ref in Pony. It has a little bit more interesting guarantee because in Java you can't prove that other people aren't reading from it. You can't prove that they're not.